Okay, so we've looked at intrinsic semiconductors and extrinsic doped semiconductors. We saw how we can create a p-type semiconductor using external dopants as well as an n-type. By themselves, p and n-type material are no good. They're simply there. If the doping is heavy, it could act like a metal, but it doesn't do any good without opposing p and n-type material together. Okay, so let's see what happens when we have both coming together. All right. So what we have here is a p-n junction. So you have a p-type material. When you bring it in close proximity to an n-type material, and it comes into contact, it's a junction that is established at the meeting point, and that junction is simply known as a p-n junction. In fact, to fully call a diode, we would say it's a p-n junction diode. Okay, so it's a junction diode. In real life, though, we don't fabricate or create a p-type semiconductor separately and an n-type semiconductor separately, and then we don't physically bring them into contact. IC fabrication, we start with a silicon wafer. The silicon wafer could be an n-type or a p-type. And then if you want, we could implant some more n-type materials in there. Then let's say this is the n-type silicon wafer. This is looking at it from the top. So this is the top view. And then inside this silicon wafer, you would create a p-type semiconductor. Okay. So looking at it from the side, if I was to take a cross section of this, it's going to look like this. Okay. This is the n-type silicon wafer. And then your p-type structure is here. It doesn't go too deep. Even this size is exaggerated in the z direction. So if this was, let's say this is y, this is x, then this going down is z. Okay, the top surface is simply less than 1 or 2 microns, probably not even that deep. Okay. So we have our structure, we create a, we have an n-type structure, we create a p-type structure inside it. And so at the junction point, we now have a p-n junction. Okay. That is defined or known as the metallurgical junction. That's the junction point between the p and n-type materials. Okay. Now, in order to make contacts, we implant aluminum or any other kind of metal to make contacts. So that again could be in a small area. That's something new. And so these would be small metal contacts. I'm just pointing this out because for explanation purposes, we never use something like this. We always use a diagram that looks like this, okay, for explanation purposes. But it's also helpful to know how the physical structure is laid out. Okay, so we have the p-type material, we have the n-type material. Now, to make it even more confusing, the notations use subscripts, and we use subscript notations with both the p side and the n side. And so if you have NN, it stands for the number of electrons in the n-type semiconductor, Pn stands for the number of holes in an N-type material. The subscript N refers here. This subscript N refers to the type of semiconductor. Okay, same thing on the P side. You have NP and PP. They both refer to the number of holes and number of electrons in the P-type semiconductor. Obviously, in the P-type material, you have an excess of holes. So you have acceptor. Excuse me. And on the N side, you have an excess of electrons. So you have donor atoms. The positive terminal is marked as the anode, negative with the cathode. Symbol is labeled right here. That symbol stays the same. Sometimes acronyms are used as A and K. Okay, A and K. These are simply contact pads, metal contacts. The aluminum, copper, gold, etc. All right, so what happens? What exactly is going on at this junction? So we'll go a little bit into electrostatics to look at the device physics, okay? So let's say we have a structure and this structure has P on the left, N-type on the right. Now, on the x-axis, we are showing how deep it's going into the junction. Not the junction, sorry, into the semiconductor material. And here, showing how deep it's going in the opposite direction for the P-type. Okay. So again, this is simply a two-dimensional schematic, but not a physical representation. So this refers to the N-type. This refers to the P-type. The doping on the N side is 10⁻16 atoms per centimeter cube. On the P-type is 10⁻17 atoms per centimeter cube. Okay. And then obviously, as it crosses the boundary, in the N-type, the number of holes are drastically less. So it's only 10⁻4, whereas on the P side, number of electrons are only 10⁻3. Okay, see that these are random numbers provided in the example. Okay. But in an N-type material, you have high number of electrons that dips as it crosses the junction. And a P side, you have high number of holes that dips as it crosses the junction. So this basically is telling you the number of free charge carriers in the semiconductor material. Okay. Also, what it's showing you here are the majority carriers and the minority carriers. So if I was to draw a boundary like this, these are the majority carriers. These will be the minority carriers on both sides, which is, of course, the answer to the last question on the quiz. Okay. So far, so good. Okay. So what is happening? There's lots of things that are going on here, actually. So when you have this crossing at the junction, What is happening is, well, there are 2 or 3 different effects, but the first effect that we're looking at is diffusion. Remember, we spoke about charge carrier diffusion because of gradient concentration. So on the left side, we have excess of holes. Those holes are going to diffuse through the junction, cross the barrier, and go over to the other side. From the other side, we have electrons. There's an excess of electrons on the N side, dearth of electrons on the P side. And so the gradient goes this way. Electrons are now going to diffuse and cross the barrier in the exact opposite direction. They are both crossing over in a bid to even out the distribution. And that was diffusion of the carriers. You all with me so far? Okay. Holes are crossing over from the left, going over to the N side. Electrons are crossing over from the right, going over to the P-type semiconductor. They are both crossing the barrier. They're both crossing the junction. In a bid to even out the distribution. That is the diffusion, right? Diffusion currents. Now, if this continues unabated, meaning if it's not stopped, what do you think is going to happen? It's going to be evenly distributed. You have equal number of holes and electrons on both sides of the junction barrier. Technically, the junction does not exist anymore. Right? That's what you would expect to happen. But that's not what happens. After a certain point, this diffusion is stopped. So researchers and analysts, not analysts, researchers and scientists who are working at the time, they postulated theories as to why this is happening. Right? So diffusion starts, but then it's stopped after a certain point. So what exactly is going on? Well, the charge carriers are diffusing through the junction. So let me write that down here. Charge carriers are diffusing through the junction, gives rise to a small current. This is done in an effort to balance out the charge distribution. Okay. To balance out the charge distribution. All right, now we come to the main explanation point. So on the left, we have the p-type, on the right, we have the n-type. What happens when the electrons and the holes leave their atom? They're leaving behind charged or ionized atoms. So when an electron leaves, it's going to leave behind its charged ionized atoms. So it creates this space right here and right here close to the junction, which is both positively charged in the n-type and negatively charged region in the p-type. This is due to the atoms that are fixed in the structure. They're unable to leave the lattice structure. They're fixed, and thus localized charges appear in that structure. And so we have a region right near the junction where it's positively charged in the n-type and negatively charged in the p-type. Opposite charges, because electrons have now diffused away and holes have diffused away. This region, because it is charged, is known as the space charge region. And because it's charged, an electric field appears. And because an electric field appears, and you have charged particles that are subject to this electric field, what happens? This electric field acts on the free charge carriers. So now the charge carriers are drifting in response to that electric field. This electric field is built in. Okay. But it's now opposing further movement of those charge carriers, and hence they stop diffusing. So they begin diffusing. That diffusion itself gives rise to a space charge region. Because this space charge region appears as negative and positively charged, it causes a charge gradient, gives rise to an electric field. This electric field opposes any further movement or any further diffusion of these charge carriers. Hence, the process stops and it reaches an equilibrium. Okay. So we'll talk more about this. Okay. We'll end class here today and we'll pick up here again on Wednesday. Read through chapter 3. I will post the reading assignment. But if you want to get started early, read through it and then have your questions ready for next class.